everybody. Please welcome George Hart.
Thank you. It's a pleasure to be here. My mic is on. You can hear me in the back? Say yes? Yes. Okay. It's just really wonderful to be here and see so many people enthusiastic about so many interesting topics. I'm going to tell you about 4 things that interest me. Have four topics sort of combined into... Oh, wait a minute. Oh, okay. I have 4 topics. This isn't quite the presentation. The presentation on my laptop seems to have died. My laptop, the mouse is frozen, but we'll manage here. So I have... I want to tell you about sculptures in general. I like to make mathematical sculptures of various sorts. And I'll talk about one in particular, something called Comet. This is a large sculpture that I made at Albion College, not that far. And then I'll tell you about the Museum of Mathematics. So the Museum of Mathematics is opening up in Manhattan in a year and a half, and it's going to be a fun, cool, interactive, hands-on place to play with mathematical ideas to get people involved in mathematics. So I'll just sort of put these together into one talk. These slides are not exactly the ones I thought I had, but these will be fine. So to begin with, in terms of sculpture, I'm enthralled by mathematical ideas, by geometric forms. I'm thinking about them all the time. And I like to take various ones and put them together as in a physical, hands-on way that people could look at them and think of them and ask themselves mathematical questions. So you might say, what do I have here? And what I have, in fact, is called 72 pencils. And these pencils are joined together in a particular way. I'll show you another instance of it. So this is the same geometric structure. In this case, you're looking straight down one set of 18 pencils, but there's 4 different directions that they come from. And the kind of question you might ask yourself is, what's the shape inside? So if you were a mouse inside this room, where would you be living? What's the space like? Does anyone have an answer? Anyone have an idea? Is it like a cube? A sphere? Well, a who? Actually, it is a kind of dodecahedron. It's not a regular dodecahedron. It's a rhombic dodecahedron. So I didn't really expect you to know that. Unless you're a geometry nut, you wouldn't be familiar with a rhombic dodecahedron. But the rhombic dodecahedron turns out that it has these 4 different directions that have a kind of a hexagonal cross-section. So these hexagons are lying along some of these edges of this rhombic dodecahedron. It's a very interesting shape. It shows up in lots of applications in crystallography and in many situations. I just like the shape. I wanted to do something interesting with it. It turns out turning into the sculpture. So here it's all done in one color. In this version, it's a little more artistic. This is sort of in CMYK space. These are 4 colors that are used in the printing process. If you're a designer of printing things, you're sort of familiar with how you can mix these colors to make any color ink. And as you turn the sculpture different ways, you can hide one color or have one more than another. If you're looking straight down the yellow axis, you won't see any yellow surface. You just see the others. So you can sort of dial different colors in this space depending on where you stand. If you kind of stand back and squint, you get some mixture of those 4 inks. So each of my sculptures has a sort of a mathematical part, has a physical part where I think about these shapes, and then it has sort of an artistic side, engineering side, how I put them together. I won't be able to say all those things about all these sculptures, but I'll get you started on some of them. So this is a big ball of CDs. Do you recognize the shape here? Anyone want to shout out the name of that shape? A soccer ball shape, yeah. So if we translate that into mathese, we call that a truncated icosahedron, but it's a soccer ball. So a soccer ball has 12 pentagons and 20 hexagons, and the openings here, you can see in this case there's a pentagon. There's 5 of these sort of pink ones and 5 of the silvery ones. Here there's 6. There's 6. At each corner, you have 1 pentagon and 2 hexagons everywhere. So if you just follow those local directions, always put 1 pentagon, 2 hexagons together, keep doing that, you'll end up with the soccer ball or the truncated icosahedron. So then the question is, how do I put these CDs together and glue them, et cetera? Those are sort of the engineering questions. Artistically, I was very surprised after I built this. It has this wonderful effect that it looks like they're glued to a sphere. Your eye just imagines that there's a sphere there. And it's wonderful that you can sort of put your hand through the hole and it's like it doesn't hit anything. It's like, oh, that's magic, that there's no sphere there. You have to see it in person to experience it. So that was sort of a surprise. And often I have a kind of a surprise. I design my sculptures from one perspective, and then I build them and I see them from other angles, and I'm often happy with them. So I'm going to quickly go through others because I don't have too much time. So this is a sphere inside a sphere. See a cavity inside a cavity? That's a little joke there in the title. This is illustrating duality. So the inner set of toothbrushes forms a, what does that form? It forms an icosahedrodecahedron. The outer one forms its dual, the rhombic tricontahedron. And when they rotate, so the inner one's on a separate string, it can rotate inside the outer one. And when it lines up in a certain spot, they're in this dual position in which the edges of one are orthogonal to the edges of the other. And again, this is sort of important mathematical idea, but you see it visually here when it's gradually churning in the air currents, and then you see a spot here where, for example, every blue toothbrush on the inside is perpendicular to a blue toothbrush on the outside. And similarly for each of the other colors, there's one on the inside perpendicular to one on the outside. The edges are orthogonal and crossing each other at the midpoints, and this is the position of duality. Yeah? Right, so the engineering is, if you're a person who actually likes to make things, then you have to wonder, how do you make these things? So what I'm showing you are final results, and the final result is usually the simplest, easiest part compared to the many, many stages beneath this. So, in fact, I had to make a rig. I had to hold everything together, glue it, then take the rig apart. And then I had to have the inner one inside the rig for building the outer one, and build it, glue it, and then take the rig apart through all the holes of the outer sculpture. So I had to make a very complex rig that had the right shape that could be disassembled. So there's a good engineering problem. What would you use to do that? I could do it in the fourth dimension, yes. I'm working on that. But I only have three-dimensional jigs at home. So what would you do? Like, you have to make hundreds of little wooden pieces that you screw together and then build it and clamp the pieces to and then wait for the glue to dry, then unscrew them and take them out? That could work, but it would be a lot of work. I found a way that's a little bit simpler. A balloon would be good, maybe. I did not use a balloon. It might be too flexible. On some other things I can tell you, I've made cardboard models, paper models, like heavy paper, cover stock sort of material, and then build something, tape pieces to it, clamp them together, and then when I'm done, soak it in water till the cardboard turns to mush and it comes out. But I didn't use that on this one. Yeah? That's an interesting idea. I don't know if the acetone would hurt this particular plastic. So one issue was getting the right plastic. So the world of plastics is full of all these things that only chemists understand. Some of them glue very well, some don't. For this particular one, this was commissioned by a dentist in New York for his waiting room. And he's able to get free sample toothbrushes from different manufacturers. If you're a dentist, they'll send you anything you want. So we spent about 3 or 4 months in which he was getting samples from all different brands. And I would do glue tests to see how strong they were until he got one that I really liked. There's a little speckle in the handles here. You can't maybe see well in this photo, but it has a nice optical properties. And it glues beautifully with a solvent cement. So you put two together and you put a drop of glue and it dissolves the plastic, then it evaporates so it becomes one piece of plastic. So for this particular plastic that dissolves really well in the solvent cement that I wanted, I don't know if the acetone would hurt it. So what I in fact did is I used a commercial building toy. There's various construction toys out there like Legos, and I used it to build this jig. Then I clamped everything on with hundreds of clothespins to get everything in the right positions, and then glued everything, took off the clothespins, and then was able to reach in through the holes and remove the pieces of this construction toy. So I was able to find a commercial product that had many hundreds of little pieces that I needed that fit together to give me a scaffold close enough to clamp everything to it. So that's sort of the engineering side behind each of these. But if I spend this much time on every single sculpture, we won't finish. But I am very happy to answer questions. But I'll mainly kind of whiz through them. So this is a series of things I made with CDs, where it cuts slots in the CDs and it becomes a kind of a tinker toy. The geometry of this is very interesting to me, but this is not, I won't say too much about that. This I like because it has 4 colors, and the 4 colors surround each hole. So there's these pentagon openings, and each one is surrounded by all 4 colors. Each floppy disk. Oh, do we know what floppy disks are anymore? I mean, I've discovered that that they're, even though it's still the save icon on like Microsoft things like, click here to save, it's a picture of a floppy disk that young people don't actually know what that's a picture of, so it may not be very iconic. But anyway, there used to be this thing called floppy disks. And so there are 5 colors. Each one has 4 slits in it and is penetrated by the other 4 colors. So there's some interesting combinatorics here of how that works. It turns out that there's 2 possible solutions to how to do this if you work out the combination. And I've made both. And they're not mirror images, though. They're different combinatorial ways. Has to do with the fact that this tetrahedral group is sort of a subgroup inside the icosahedral group. This is made of knives, plastic knives. This was my first concept for a part of a sculpture that has knives, forks, and spoons. This is a larger CD construction. This is at UC Berkeley in the computer science building there. It's about 2 meters in diameter. Again, there's a geometric aspect of it that interests me, that there's these kite shapes in various ways, and there's also equilateral triangles. It's easier to see in person, but this is all hanging from a chain, and it spins slowly. There's a close-up that may be able to see it. So I was able to cut the slots in all the pieces, test fit it at home, put all the pieces in a 1-foot cube box, and mail it out to Berkeley. Then I was able to show up, and they said, well, how long do you need to build it? And I said, well, I could build it at home in 4 hours, so maybe over there, since it's an atrium and I'm going up and down in a lift, maybe it would take a few more hours. But ended up going there 2 days before the opening event, gluing all these little modules together the first afternoon, letting them harden, and then going up and down on this lift that took the atrium starts at the 6th floor and it goes up to the 8th floor, and had to bring all these pieces up and hook them up in position, tie them together in sort of in the air up there, hoping not to drop too many, and get it all up in another 4 hours on the second day. So I've done a bunch of things with CDs. So it turns out CDs are now sort of disposable items. At that time, I had to actually go around and think about buying CDs until I found some company that was willing to give me their leftover, the previous version of their software kind of thing. But now you have thousands of cheap CDs. It's fun to put them together. The kinds of glue that holds them together are not safe for use in classrooms, but I worked out this technique where you can overlap 2 CDs and put a cable tie through them and pull the cable tie tight, and it joins them together. And I've done various workshops. Here's an example of one. This one, I think, was in Kyoto a couple of years ago. But there's all different shapes you could make. So again, here's this truncated icosahedron. And there's just lots of these cable ties holding piece to piece, so you can do this in a modular way. This is a slightly different shape, related to that, but different. So there's lots of interesting forms you could make. The trick is that you can't have too small a form, or the CDs are too curved and they snap. And you can't have too large a form, or the cable ties don't really hold them, and it becomes sort of tall. But there are some fun things that you can make sort of a big sphere, but it'll hang and sort of become a tall sausage thing. But then if you spin it really fast, it opens up, and then as it slows down, it comes back small. So there's ideas here for sort of dynamic things you can make that are fun and very inexpensive. If you just get everyone in your class to come and bring their old CDs from home, you can get a stack of them very easily. They chose nice color ones because this was as part of a museum exhibit at the University of Kyoto. So I'm going to show you a series of pictures of sculptures that have flat pieces. So this has a kind of a brass knot going through it, but it also has these flat pieces. So modern technology happens to make it easy to make flat pieces of interesting shapes. There's all kinds of computer-controlled laser cutters and plasma cutters and CNC routing machines, etc. So this I did on a routing machine. This is a big table. You can put sheets of plywood on it, and you can draw a shape on the computer, and you can say, go cut it. And the computer draws with a spinning blade that cuts out the wood any place you like. And so I would cut around these shapes and have them very accurately, very relatively easily made. And then I would do some beveling of the edges and put it together. So this was the first thing I made that really had a lot of flat pieces and done on a computer-controlled machine that led me then to think about really working in that direction. Given that that's so affordable for making complex pieces, what can I do to sort of go to the edge of that technology? I had been at the same time, these are all from maybe 10 years ago, this time period. These are done from flat pieces. These are parallelograms, but then I heat them in the oven. So take acrylic, put it in your oven for about 3 minutes at 350 degrees, and it turns kind of soft. Have the fan on because it's kind of stinky. But then you can curve them, put it in a jig, let it cool down, and you'll have it exactly in the shape you want. So this is 30 pieces. One piece is sort of a twisting piece. And they're twisted so the edges exactly line up with, I can join them like an icosahedron. There's 30 edges on an icosahedron. The visual surprise that I like about this is that it's very exact and regular. Each piece is this perfect twist made to a very precise angle in this jig that had to hold it exactly right while the plastic cooled and hardened. But when you look through it, it becomes like a funhouse mirror thing. So the front distorts the back. As you look through it, the back is curved, and as it hangs from one point and turns, it's constantly distorting. And it's sort of this interesting optical blend between sort of a crystalline perfect form and this amorphic organic experience. And I discovered that I really like that. In most of my work, I try to blend the kind of organic aspect with a mathematical purity. Here's something based on an icosahedron. So I don't know if I'm using the word icosahedron like that makes sense. An icosahedron is one of these platonic solids. You take equilateral triangles, you put 5 at each corner, and you end up that you close over a sphere when you have 20 of them. So it's the shape of a, people nowadays know this as a D20, a dice that has 20 sides if you're playing various games that have multi-sided dice, not just 6 sides. So take your 20 triangles of your icosahedron, imagine they're all glued edge to edge, and sort of blow them apart, separate them at the edges, and everywhere 2 are joined, and I've separated them, put a half twist, like a Mobius strip in there between them as a bridge. So you have in here a triangle, here's another triangle. These were originally together in your mental icosahedron. They're separated, and I have this half twist bridge, and do all that, and make it out of steel, and then cover it in paper mache, and you have this sculpture. So it ends up having 6 of these edges. It's fun to follow these edges around, these different paths that they interweave around each other. I love wood. Wood as a material is sort of just very fun to work with. It's very hands-on. It has grain, and it has a good smell, and there's just something very enjoyable about working in a wood shop and making wooden things. This is an interesting form which has what I call tri-equilateral trapezoids. So these trapezoids have 3 equal sides, and they join up in funny ways where what you would call the base of this darker one here joins up to the side of the next one, etc. And it was quite a surprise to me mathematically that you can make something that actually closes that has this highly constrained shape. It has just equilateral triangles and these tri-equilateral trapezoids. And that this one has 2 mirror forms, and each one has a kind of a color symmetry. If you reverse dark and light, they stay the same, but you can reverse it in the mirror, and they become the opposite one. There's, again, interesting geometric property underlying these that intrigue me, and I hope to be able to make things of this sort, and some people will look at them as art, and other people will look a little deeper and begin to ask these questions, like how does this work, and why are those lengths and angles there, and how do you figure it out? To get people thinking about mathematics, because mathematics is so much more than what most people see in a classroom. In our culture, it's very sad that the joy of math has been lost. Okay, most people go through 12 years of public school, and they don't know that math is this creative, fun subject, that it ties to art, and that it's just, there's so many branches of math that you don't see in public education. So if I can get people realizing that mathematics is at least interesting for these artistic purposes, it might get them thinking deeper about it. So that's sort of my educational rationale when I pretend I'm the professor and have to have an excuse for why I'm doing this. But at the same time, I have this personal rationale that I just like making things that I find sort of aesthetically interesting. So I'll keep showing you some more of these, but I probably won't talk so much about each of them because there's too many here. But this is copper. It's a model. It's something that could be made very large. It's based on a dodecahedron. This shows a kind of a deep structure. So mathematicians often strive for abstraction. They take different things that look different, but they try and find that underneath there's sort of the same thing going on in terms of what makes it work. So these all have the same symmetry group, the same rotation group. They have very different surface materials. So this is paper mache over steel. This is coffee stirrers and Dacron thread. The stirrers never actually touch each other. They're all held off as a kind of a tensegrity structure. This you saw is this acrylic. This is just acid-free paper, cardstock. They all have the same rotation group. They have the order 60 group of rotations of the icosahedron, of different ways that I can turn one about various axes and have it look unchanged. That's what they all have in the same way. They can be certain axes you can turn at a fifth of a revolution, certain axes you can turn at a third of a revolution, 15 axes you can turn at a half a revolution. Those axes, that symmetry underlies them. So they're the same thing mathematically. It's really just one idea. It's not at all creative to make four things. Making one of them was sort of the mathematical idea. The rest is just changing the surface structure. And in mathematics, you see many things from that deeper perspective. This is kind of a sensual experience that you look at this and people have two different reactions. It's very strange. Some people just want to go immediately there and touch it and put their hands inside and feel it. And other people find it kind of creepy and just don't want to be near it. And it's kind of a nice psychology test of who I allow in my house. But there are, in fact, 6 openings from different sides that go to the inside. The people who like it see this as a kind of like a tribble, and they want to touch it and pet it. And then when you do, there's this weird gestalt shift, because it looks all furry and roundish from here. But when you touch it, you say, oh, wait a minute, there's an edge. There's an edge. Oh, wait, there's a square. There's a triangle. So in fact, it's completely geometric on the inside. If it's naked of fur, it's the shape on the left. It's made of pentagons, squares, triangles. Even on the inside, all the concavities, the 6 tunnels, they all meet through the center. They're all made of pentagons, squares, and triangles. So with your fingers, you can have this geometric experience, but when you look at it, you have this organic experience, and it's kind of cool. So go back and see if you can find those squares and pentagons. Well, you can't see them, but you can feel them. Anyway, and it's sitting on a 3/2 twist Mobius strip. More wooden pieces. This is kind of a jigsaw puzzle that can be solved 2 different ways. The left side and the right side are made of the same pieces, but they go together. They both have a 3-fold symmetry, axis vertical, but there's 2 different ways to do this. I sort of like the fact that these parts were sort of unconstrained in having these only two different solutions, and just turned them into a sculpture. This is aluminum. This is sort of an homage to M.C. Escher. So you probably know the graphic artist Escher, a Dutch artist who makes these wonderful tessellations and 3D forms. Many of his structures have this wonderfully sort of confused geometry that makes sense within its own world, but doesn't make sense as geometry. Here I was trying to create a kind of a doorway shape. These different doorways are going through each other in an unusual pattern, and yet when you look at it, it all is completely regular. Here's a close-up just to show you a little bit of how it works. Again, with most of these, and with really any sculpture, if it's a good sculpture in my mind, you can't really communicate it with a picture. You have to see it in person. You have to walk around it. Ideally, you want to sort of touch it for a while and get a sense of it. But this gives you some feeling of how it has this architectural structure, and yet not the usual architectural structure. More woodwork. I love wood. This has 902 pieces of 3 different colors of wood, arranged like a traditional Roman mosaic. I like to follow the roads, so if you start on a light road here, like this hexagon, you can follow the yellow brick road, you could turn and follow another yellow brick road, you can follow another. So you can end up going from point A to point B without having to make a right turn anywhere, except when you come to the hexagons you can turn. And in fact, you can get from any hexagon to any other hexagon through some path. They form a connected graph. But then you can do this gestalt shift and be on the dark road. So you can start at a triangle and say, can I go to another triangle and then go to another triangle, and try and find all the paths from one triangle to another triangle. And then, in fact, you'll find that there are 6 different universes, that there's 6 separate independent graphs that are not connected to each other. So I can't go from this triangle, say, to its nearby triangle here, only going straight to a triangle and then turning. And if you sort of draw out the graph of the structure, then you can see it has this different disconnected property. So anyway, I start with software. I think about these forms mathematically. As a computer scientist, I write programs. So here's that same shape as I first sort of saw it on the screen. And then I think of various ways to take shapes that I like and bring them out in some physical form for others to enjoy. So this one I turned into wood. This was many years ago, a slightly hairier period in my life. But it gives you a sense of the size of that sculpture. So I'm going to whiz along through some of these because I have more I want to show you. But this is more acrylic. Large metal sculpture. This is about 5 feet in diameter, 8 feet tall on the base. Again, interesting combinatorics. There's 5 colors. Each band crosses the other 4 colors. These are sketches for a large wooden sculpture here. This was a commission for a library. I asked the librarians to set up a voting booth where any patron can come in and write in their 3 favorite books. The librarians totaled up the favorite books of the century. This was commissioned in 1999. They gave me the list, and then I used a computer-controlled router to carve those titles and authors in these wooden books, and had these bronze donuts cast, and there's a steel rod through the spine of each book. And I brought all these pieces to the library, and we had what I call a sculpture barn raising. So I do these events where I bring all the pieces, and I invite a community of people to help me build the sculpture. So we assembled all this, and it's hanging. This is in the Northport Library in New York. The #1 book, as voted on by the patrons of the Northport Public Library, is, what would you guess? The book of the century of the 1900s. Catcher in the Rye is the book they liked. Grapes of Wrath. And Cat in the Hat is on there. There's many good books on there. Anyway, that was #1. This is laser cut steel. Maybe I'll not say too much here to give you a sense of it, but as I was saying before, this laser cutting technology allows you to make complex forms very accurately. We have here, we're going to move into a series of sculptures made by rapid prototyping. So a rapid prototyping machine, a 3D printing machine, allows you to design a shape on the computer in 3 dimensions and hit the print button, and instead of coming out on paper, it comes out in 3D. So you have several of these on campus. They work in various ways, but they somehow build a physical form from a geometric description in software. And you can make very complex shapes. So I'll show you various things. Again, these each have a story. This is a projection of a 4-dimensional object into 3D. This is based on what's called a 120 cell, a particular projection of it. These are things which would be very hard for me to build physically. They tend to be small, about 3 inches in diameter. You can make all kinds of curves. Here I'm experimenting with dyeing them. So this machine, the pieces come out white. They're nylon, polyamide. But you can use various dyes that adhere to nylon and use kind of watercolor effects to sort of get gradations of the dye, let it diffuse in to get all kinds of beautiful effects. I'll show you a few examples. This is a puzzle. I made a bunch of flat pieces. Each piece is sort of an H shape, but this H shape, they lock through each other, and you can make all these diagonal bevels, etc. The slots tilted in the right way very easily using this technology. Oops, I went too fast. I have a series here of sculptures that are made on a rapid prototyping machine that are based on ideas of undersea creatures in terms of the organic aspect, but they're also based on mathematical ideas of what's called the hyperbolic plane and tessellations in hyperbolic space. So you may be familiar with how in the Euclidean plane I have to have 360 degrees of angles around each vertex, so I can, for example, have 4 squares to make a tiling like we have in the ceiling here, but I couldn't put 5 squares because that would be too many degrees. In hyperbolic space, you have more freedom, so it's sort of a geometry of sort of saddle-shaped curves is one way to model them. But here, in fact, what we have, oops, wrong button, what we have is a square, and at each vertex, there's 5 of these 4-sided holes meeting. And in hyperbolic space, these are exact perfect squares. They're all congruent. They're all the same size. And you can do sort of rigorously the mathematics of hyperbolic space to work out all kinds of properties, but you can't actually build them in our sort of Euclidean universe. But you can make various models of them. So there's something called the Poincare disk, which is one way to take this hyperbolic space and map it into a circle. And the parts which are, in fact, all equal squares in hyperbolic space have to get distorted. They become smaller as you get to the edges. But it gives you these beautiful forms. I find them reminiscent of sand dollars. And so I've made a series of these. So these are like sand dollars. They have a kind of a curvature to them. They're thicker in the middle. They get thinner towards the edges. You can take that same idea and turn it into other 3-dimensional shapes. So as I sweep around this hyperbolic disk mapped into the Poincare disk in the previous model, so sweep around that in polar coordinates, I can look at the pattern of holes, and I can apply that to this sort of torus sweep, sort of mapping one into the other. And here I get a kind of a creature that, again, is based on a hyperbolic tessellation. I have to count here, but it looks like I have 1, 2, 3, 4, 5, 6-sided opening here, and 1, 2, 3, 4, 5, 6, 7. So this is probably based on the hyperbolic analog to the soccer ball, where each vertex I have 2 hexagons and 1 7-gon. And that's too many degrees to pack around a point in Euclidean space, but you can do that in the hyperbolic plane, have a uniform tessellation, every vertex is the same, and then turn that into forms of this sort. So these ideas I find beautiful, and I can map them into all kinds of interesting shapes. So similar idea here. This is a more complex tessellation where I think I have a pentagon, 2 triangles, another pentagon, and then another triangle as the pattern around each vertex. This is based on edges of a dodecahedron, again mapped. This one I think is 5, 4, 5, 4. So what makes a uniform tessellation is every vertex is the same. So if I look at a vertex, I have around it a pentagon, a square, a pentagon, a square. And every vertex has that same formula. And I've taken that hyperbolic idea and mapped it into this physical thing. So again, this is just about 3 or 4 inches in diameter. Has a wonderful lightness, a sense of a geometric undersea creature, letting the diameters of these parts sort of trickle out. And in my file, I design these things so it's right at the limit of what this machine can make. Each of these 3D prototyping machines has some sort of finest resolution that it can produce. And if you go finer than that, the pieces don't hold together, they fall apart. So if you go right up to that edge, you get a kind of a random failure down at the end, which again adds to its sort of organic sense. It looks like it's maybe growing or whatever. And then the coloring, again, I've done by hand. So it's dyed in yellow and also in green around the edges, with, again, working wet and sort of applying dots of dye in a wet form and letting it diffuse in to give me these interesting gradations of color. So there's many different aspects, from the mathematics to the artistic to the engineering that all blend together. This is a sort of an engineering model. I like this. If you're a geodesic dome nut, whenever you walk up to a geodesic dome, you'll look for the points that have 5-fold symmetry. So most of these outer points have 6 edges meeting them. There's certain ones that have 5 edges meeting them. In a complete sphere, there's got to be exactly 12 that have 5 points. It's a consequence of Euler's theorem. And here what I've done is I've made a 2-layer sphere. So spheres like the one in Montreal have an outer layer and an inner one, which is its dual. This is this idea I was mentioning before, where one tessellation is somehow orthogonal to the other. The edges of one cross the edges of the other at right angles. So there's an outer edge and an inner one, which is at right angles, perpendicular to this. 2 dual tessellations, they add up to a very rigid truss kind of structure. And what's unique about this is the only chiral 2-layer geodesic sphere in the universe, I'm sure. But what do I mean by chiral? It's not the same as its mirror image. So if you look at the pattern here of where the 5-fold vertices are, and you follow a line out, I start at 1, I go 1, 2, 3 hops, and then turn right and go 1 hop to get to another 5-fold point. And that's the rule everywhere. I can start here and go out in any of the directions, say 1, 2, 3 hops, turn right, and then go 1 more hop to get to another 5-fold one. This is part of a family of forms where I can specify those 2 parameters. I can go forward 7 hops and turn right and go 4 hops, and that'll be how I get from a 5-fold to a 5-fold. And these are chiral because there's a mirror image one where I would go forward 3 and then turn left and then go forward 1 hop. And you would never build these out of steel because it requires sort of twice as many pieces. It's just, you don't have the advantage of mirror symmetry to make things on the right and the left the same as each other. So you have twice as many parts in your inventory of pieces that you have to fabricate in your shop, and that much possible confusion when you're building it that you may take the wrong piece. But on a rapid prototype machine where the computer is just keeping track of all these little parts, it's trivial to make this. So it's just sort of an example of a kind of an engineering construction, and I find it much more interesting visually because it is chiral. If you start at a pentagon and you follow these paths around, how do these lines go? It's more interesting that the way they spiral than the ones that you would physically build. So this technology lets you sort of make things that you could build in principle, but you just wouldn't. And I sort of like that. So again, I have quite a series of different forms. This is small. This is in a time capsule at Stony Brook University. Someone's going to dig this up in 50 years. Here's a close-up of how it works. Again, there's a story to each of these, which I don't want to say too much about, but this one I kind of like. So this is sort of chainmail. This is all built in place. I forget the exact number, but I think it may be 5,000 or something, little rings that go together. You could take pieces of wire and bend them together. If you're a chainmail sort of anachronism person, you could build this. But this is all built in place, assembled on a rapid prototype machine. This is about 6 or 7 inches in diameter. And if you look hard, you'll find there's certain places somewhere in here where there is a ring that has 5 links. And I'm trying to poke around and find one. Should be one right about here. Maybe it's in there. But most of the rings, these circle rings, have 6 neighbors. Again, Euler's theorem tells you that there's going to be certain places that have 5 neighbors. This whole thing would just collapse like a sack and be flat if it was all chainmail that was free to move. So what I did is I made certain parts of it that you see rigid here. I made the chainmail a little thicker so that it locks together and it becomes rigid. I think I have a picture of it. Oh, here I have a picture of it close up. Here we should be able to find a 5-fold place. Can you see? Yes, I see it. Do you see the spot that has only 5? There's one ring with 5 neighbors, one of the circle rings. It's right here. And all the rest have 6. And this is in the center of each dimple. So what's happening is on the right in the blue, we have parts that I made rigid together so that they don't collapse. They form a skeleton that holds the rest up. These dimples in the center that are shown as red here, those are designed to be free. And as you shake it around, they move, so that no matter how you turn this, the top half dimples in, and the bottom half, the chain sags out to form a sphere. So the top half dimples in no matter which way you turn it. And it's kind of a beautiful thing that you can make so many parts, and it just comes out of the machine already assembled, already built. So let me just say at this point that these technologies are really liberating in that they let you think of new things. They're also a bit humbling because if you think about this process of what computers can do, all the software that you can write that processes this, I don't know how many millions of little triangles in the actual mathematical model of this. You can process things that are incredibly complex. These machines are very patient. It may take it several days to build this, but the machine will just go at it and build until it's done. Certainly much faster than you could do it, and that you can build anything nearly that complex in the same 2 days. And if you think about this whole process, and what's the limit, what's the bottleneck? The bottleneck is you. It's your imagination. Okay? So the human imagination is the real limitation in terms of what you can make with these things. So as more people use these, as more ideas come about, as we share ideas, you're going to see cooler and cooler things that people are making on these machines, because it's just a question of people getting into the right mindset to understand what they can do. And really there are no geometric limitations other than sort of small size of details and the maximum size of the build chamber. Other than that, it can make anything. So it's sort of up to you as the next generation to be coming up with great ideas what we can do with this technology. I have a number of other things I've done here. So I've mentioned that I like to do barn raisings where I bring a bunch of pieces and have people build things. This is a barn raising, this is also in Kyoto, where we took, I forget how many, this is about 5,000 pieces of a product called Zone Tool and built construction. This is really nice for making certain families of 4-dimensional polytopes. So this is one I did in Central Park. I just brought, this is about 6,000 pieces, brought it into Central Park, had a lot of people come and help me build it. We built it there in the grass, and then we put it on display. Here's part of the construction. And it was just cool that people from all around the world who were visiting New York would just come by and look at this thing and talk about it. It's really a wonderful way to take sort of ideas of mathematics or whatever it is that is your particular passion and sort of get a group of people involved in it. Try and find some way that you can get people to help you make something, display it for a while. And so we had it out for the afternoon and then took it apart. It's kind of fun that, these people would come from France or whatever and they say, what is this? And you say, oh, don't you do this in France in your parks? Yeah. These are more laser cut pieces. I'm going to zip a little faster here, I think. Many of the... Sure.
It's pretty complicated. So you had to know how to build it, but it doesn't look like it would be easy to manage people building it.
Yeah, that's another fun thing. So as I do more of these things, I'm learning much more about working with groups of people and organizing things and sort of the joys of leading a bunch of people into these. I had never built it, so I mean, mathematically I understood it. So there's certain, in one sense it's very, very simple. It's one basic unit repeated again and again in 4 dimensions. So if you can visualize this 4-dimensional model of it and that it's then projected to 3 dimensions, it then gets, there's a kind of a transformation that foreshortens pieces. So there's a whole range of different parts, but the underlying structure it can be broken down to certain modules. So I was able to get people to build these modules. And on my website, if you poke around georgehart.com, you'll find sort of step-by-step activities here. But I was able to get these 50 people sitting on different picnic blankets to each build a pile of these modules and then to bring the modules together and build them. So I had this kind of parallel processing scheme designed. And along the way, I'm sort of running around from group to group trying to find little mistakes or giving them tricks to work faster. But what you're sort of saying is that, in some sense, I didn't know how long it would take, how it was going to come out. I mean, it was an experiment, and all of my constructions are experiments. And that's sort of the fun. That's the real excitement. Like, what have I not thought about? I've tried to think about everything. But in fact, this may be the first time the structure is ever built. I've repeated many of these workshops. Some of them are easier than others. So I've built some of these. This is a product called Zome Tool, and I've worked with it all around the world. I've done activities many places. And some of them are sort of down to the point I can do a kind of a cookbook, a simple, if we want, like a 2-hour construction. The larger ones that I've only built once are very much an experiment. But I like that. It makes sort of life exciting. So I have some other pictures I'll show of some such constructions. I want to zip through some of these. I'll say that many of these are puzzles for me to build. So I designed them on the computer. I can sort of rotate them around. I know how they're going to go together. I can send out the file to be laser cut. And then I get the pieces and I have to actually assemble them. And that can be really hard. This was a barn raising. This I did at MIT. I was artist in residence there a few years ago. And we laser cut the pieces there and had a group of students put it together. And again, I didn't know how long it would take. It ended up taking a couple of hours. Everything worked out. But I always worry about that. So let me whiz through these and come to a different set of things. This is plasma cutting steel. This is fun because it locks together without any connectors or glue or screw. So this is designed at the mouth of the snake. They meet in groups of 4 that locked, groups of 3 that lock together like at right angles, like a corner of a cube. And these notches in the back. I'm losing my laser here. Okay. These notches in the back sort of hook together in pairs, and you have to kind of bend the last piece to get it in, but then it locks together. So this is a similar idea with paper. So here are 60 pieces of paper that you add 2 of these 3-shaped parts together, and they form an 8-shaped piece, and they all interweave. This took many, many hours for me to put together. But no glue is needed. It all kind of interlocks. Similarly, but in steel, powder-coated. Much more complex, but interlocking again without any welding or brazing. So this has little pegs. So, oh yeah, so if you're old enough computer scientist, you know what spaghetti code is. If you're a younger person, you don't know what that means, but that's okay. I won't explain it here. Anyway, so this was a wooden version. This is 1 meter in diameter. This was sort of a prototype laser cut wood before investing in the cost of building this one, which is laser cut aluminum. Again, done as a barn raising. This is designed as a puzzle. This I wrote a little article for Make magazine. So if you like to make things, there's sort of a growing movement, which I find wonderful, of people around the country who like hands-on construct things. There's a magazine called Make, which is all about making things, whether it's make it out of wood or high-tech out of microcontrollers, whatever. And they have these maker fairs in which people get together and show how they build things. And I've written a number of articles, and now I write a weekly column for the Make magazine online. I'll come back to that. But instructions for making this are in an article in Make magazine. This was a stainless steel piece, laser cut, that I did at a conference where I had a lot of people help me build it, put it together. I'm going to whiz through some of these just because I don't have time to explain them all. This one I'll just say, this sculpture fits inside this, has this piece, and it fits inside that shape on the left, which packs together. So I can take copies of that sculpture and pack them like blocks in all different forms. And here are examples of that. This is just ideas. I'm always sort of thinking ahead of what I'd like to build on future sculptures. And the pieces also go together a different way. I won't say too much about that. More with puzzles. Okay, so I want to talk about one sculpture in a little more detail. So each of these have, as I said, a sort of a mathematical story, an engineering story, a person story of how we build it. There's jigs, things that you don't see, or whatever it is. This sculpture I'll show you step by step is the largest that I've made. This was a commission for Albion College in Michigan. They invited me to go give a talk and look at the space. And I went there and I said, this space is too big. I can't make something that big. I don't know how, or it wouldn't be safe, or whatever. So we spent some time and we ended up deciding that I could make 9 separate sculptures that sort of move across the space, that together make one space. So I think of them as slices in sort of a 4-dimensional sculpture, if you like, or as a morphing, changing from one end to another. There's 9 different forms, but they each relate by this continuous transformation. So this was done, I guess about 2 years ago now, as a group assembly, and I'll show you the steps. So here's the final sculpture. It changes from yellow down here at the far end through shades of orange up through deep red at the near end. It's in this beautiful atrium space that has lots of stairways and walking, catwalk kinds of places, so you can see the space from all different angles. It's architecturally very interesting. And so here is how I first set up. I got balloons and tied them to chairs, helium balloons, and laid out where I wanted the sculptures to be so that as you walk up the stairs, you have a sense of it sort of following you, and it comes up here and it comes up really high. There's a couple more behind the camera. And marked out, measuring the XYZ coordinates, how long is the string, so that I could tell the building people where to hang the 9 chains. So that was done ahead of time. The chains are sitting in the ceiling. I designed the form. Here's just a computer rendering of one of the forms. But in software, I'm sort of working out what are these shapes, how do they interweave together to make a nice form. So each of these has an inner part and an outer part, but they actually lie in the same planes. That if I follow one of these inner parts and follow it out, like this part here that goes through connects here. These are all coplanar, and it comes out to there, so that there's 30 different planes based on the planes of a rhombic tricontahedron. Made a little paper model. So when I made this paper model and brought it there so I can show it to the people at the university, and basically this was my way to sell them that they'll like this. So once they saw this, they said, yeah, that's really cool, go build it. And this is indicating the inside and the outside, not the final color choice, but indicating the geometry of it and the richness of it and how it's made out of parts. So if you want to make really complex paper models, by the way, there are very affordable new technologies, various kinds of vinyl cutters or paper cutters, that you draw a shape on the computer, you hit print, and it has a moving knife that follows that path and cuts out all these pieces. So I did not have to sit down with an X-Acto knife and cut out each of these shapes. I can basically hit print, and the little machine goes, and out comes the pieces. So explore that if you want to make intricate paper models. So I had the laser cutter test fit about 10 of each piece, so I can put them together and make sure I didn't make some terrible mistake before spending the money on the whole set and powder coating them. So we got these sample parts and bolted them together. That's David Riemann, the chairman of the Math and Computer Science department at Albion College, who really championed this and did the internal sort of work with the deans, et cetera, to get this all approved. And we bolted these pieces together. Everything seemed to fit just fine. So I had the whole set cut, sent them off to powder coating in there's all different shades of colors. Brought the pieces to the university, and we had announced, come to the sculpture barn raising. So here we have all the pieces being assembled. Each table is working with a slightly different form. I had to sort of prep some people that were the group leaders for each table. They're working on the inner spheres here. There's various brackets and lots of nuts and bolts. All different people came. A lot of students, but people brought their families. Faculty came and brought their families. So up in the ceiling here, you can see the spots where the chains are. We put a little picture on each chain of what the piece is going to be. We're building more or less underneath each place. And here we're finishing the inner sphere. As I said, there's 2 layers. And we took some pictures of the inner piece. There's a couple of extra pieces of each one. I always worry, is some piece going to get broken, get lost, is someone going to walk off with one? So you make some extras. But I've never had any trouble. I mean, I've never had missing pieces, but there's so many things I have to plan for and think about. Then we come to the second layer. So there's 60 more pieces that form the outer layer of each of these, and plus these brackets, and here are already connected. And then we begin this really intricate weave. It's a complex weave. It's different on each one. So the pieces on one end, the sculpture, the yellowmost one at the far end, they start out as an icosahedron and a dodecahedron in a kind of a dual position. And when you come to the next one, there's a little bit of a deformation and a kind of a link, and then another deformation and a link, and another deformation. So by the time you get to the end, it's very far removed from that. But we'll zip through the different examples here. But each one can be derived from the previous one by a small transformation, by an extra hole beginning or opening or enlarging, so that by the time you get to the end, you have a very different form from the start. And I like that as a kind of a metaphor for sort of mathematical derivation. That, what mathematicians like to do is have a kind of a certainty when they give you a proof where they say start from some very acceptable basic axioms, premises that will agree as a starting point, and do a step, and by a series of operations you end up with something which is surprising and different, but you can go back and see the progression. So I tried to have a metaphor for that in the sculpture, that by the time you come to the end here, this is this ornate flower, interesting thing, but you can walk back step by step, follow the colors and the shapes back down to the beginning, and you'll see an icosahedron and a dodecahedron. Here's this pattern of shapes starting from the top and how they slightly morph if you just take what is the form for the 9 different orbs from the beginning to the end. So you can see the gradualness. And this also helps you visualize it as, in fact, could be seen as a 4-dimensional object, where this is a continuous morph from one end to the other, and we've sliced it into these particular 3-dimensional cross-sections. Here you can see some eyes. So we moved some of these screws, put in these eyes, 3 chains go together, and then using a lift, the building people was able to bring them up to those chains. And the whole thing was built in, I don't know, about 4 hours, no problem at all, for everything altogether with 18,000 parts. Okay. Say again? How many people? They came and went during the day. Certainly more than 100. I don't know if it was 200. But at any given time, there was typically, 6 or 8 around each of these tables. Let me tell you about the Museum of Mathematics, and then I'll tell you, I think, about one more project coming up, which in my other set of slides I had blended in already before the museum part, but I can do it afterwards. I've been a professor most of my adult working life and really enjoy teaching and working with students and projects and sort of the academic life. Professors do various kinds of consulting and outside jobs as sort of part of what allows a professor to be current between the time that they're teaching. They try and do other things that keep them at the forefront of their knowledge. And what I've been doing is involving sculpture and modern construction techniques. For the past 2 years, I've been working with a group of people forming a museum of mathematics. And this has grown into such an exciting project that I've made this leap. I resigned from being a professor as of the beginning of September, and now I'm working full-time at the Museum of Mathematics. I want to tell you about this. In some sense, to me, it's like making a big sculpture, but a much, much bigger sculpture than anything I've ever done. But it's this concept of creating a hands-on, interactive place. So you've been to many science centers where there's all kinds of, tornadoes or whatever. There's things that you can play with and interactively learn about science principles. There's no museum of mathematics like that. There's no place that you can go and get excited about the joys of math, the creative side of math, the fun parts of math, the richness of math, which you don't see in so many other places. So in university level mathematics, you're learning about graph theory and group theory and game theory and all kinds of things that are not out there in the public. We want to take some of this richness of math and get it to people starting when they're young, but also provide it to people of all ages in an engaging, fun way. And there are some museums of mathematics in Europe and in Asia, but there's none in North America. So we're creating the first one. We've been raising millions of dollars, and we're going to open the space in Manhattan in about 1.5 years, in 2012. We sort of got our feet wet in this by creating something called the Math Midway. The Math Midway is a traveling exhibit. It's got about 20 exhibits over 4,000, 5,000 square feet that is now visiting different museums around the country. It opened 1.5 years ago at the World Science Festival in Manhattan. It's based on what we've learned from that, we're now building a 20,000 square foot museum. So there's a group of people. Glenn Whitney there on the left has really been the spearhead behind this project. Cindy Lawrence is our chief of operations. That's me. Tim Nissen has joined on since this picture. He's our chief of design. We have staff. We deal with outside fabricators to actually build things for us. We have an advisory council of generally academics around the country, people in universities who are interested in innovative ways of communicating mathematics, to work with and talk about content. My title is Chief of Content. I'm responsible to make sure there's good math in our museum. And we have a board of directors. These are the people who are more responsible for the financial health of the museum. This is an example of one sculpture I designed that's part of this traveling exhibit. So here is our premiere. What you have in the center is a three-wheeled tricycle that goes around, but the wheels are square. But it gives you a perfectly smooth ride because there's a particular compensating shape to the track, which it turns out if you solve the right differential equation, a track which is a catenary curve inverted will allow a square to roll over it where the center of the square remains at constant height. So the tricycle that rides on that axle at the center of the square has a perfectly smooth ride, even though when you stand next to it, you see the square rotating. So we have several booths here that have high-tech things inside them, computer-based, whatever. I'll show you a few pictures. Lots of outdoor things, a big maze to walk through. So this is what we call the Math Midway. Here are these tricycles. And you can see that we need, in fact, 6 different sizes of wheel. So there's a small kid's trike on the inner track, and then a larger adult trike on the outside track. And as you go further out, the wheels have to be larger because they have a larger circumference in proportion to that same to their radius. We design signboards that try and convey some mathematical ideas to how the fact that you can start with any shaped wheel, you can solve for the compensating track. We have a number of exhibits. I'll briefly say this one solves a problem where you pick a point to start a car rolling down a track, and you pick a point for it to end. And once you fix those 2 points, there's this mathematical optimization question of what track allows the car to roll the fastest. So a straight line is the shortest path, but it's not the fastest path. It turns out that if you go down and then across, you pick up speed here because you're going down, and even though it's longer, that speed carries along and you get to the end faster. So the question of what is the fastest possible shape is an interesting problem. This was an important problem in the development of the calculus of variations in the 1700s, actually the 17th century, 1600s. And it turns out it's a cycloid. And you can experiment. You can move these pylons up and down. You push the button, this car rolls, a little timer tells you how long it took. And you can keep adjusting it until you find one that you think is the fastest. You can, in software, display different curves there. You can, on the flat screen behind you, you can display a parabola and a cubic and a cosine and others, including the cosine, including the cycloid, and find out that, in fact, the cycloid gets you there the fastest. So, again, this is sort of a hands-on, interactive way to sort of explore with mathematical ideas. This is kind of cool. We have these 3 spinning objects. You look at them. They're surfaces of revolution. So this one on the left is this hyperboloid surface. And then when you push the button, they stop, and you can see what's generating them. So that beautiful smooth curve is, in fact, formed by a single straight line. If you take a straight line and you kind of rotate it around, and I rotate it about an axis which is skewed to the line, you get this nice curve. This one in the middle is a cube standing on a corner, and on the right you have a cylinder. It's formed by 3 different cross-section slices that are ellipses. So when it stops, you can see the individual pieces. When it spins around, you have this sort of guessing game. This is a slice object. So we have this plane of laser light. There's a ring, there's these lasers in it with lenses that diffuse the laser into a plane. So if you put something in there, you'll see a line of the cross-section. You can put your face in there. They're eye-safe lasers and get sort of contour map of your face as it goes around. So if you put a cube in there, one way to hold it, you slice a square cross-section. If you put in just the corner, you slice a triangle cross-section. If you put the cube in just the right way, you have a hexagon cross-section. So it turns out there is a regular hexagon in a cube, 6 equal sides, 6 equal angles, 120-degree angles. You have to know how to slice it. You can explore and find that. Okay, if you take a tetrahedron, a triangular pyramid, there's a way to slice that that has a square as its cross-section. And again, when you look at it, it's sort of surprising. How can there be a square with 90-degree angles in this thing made out of 4 equilateral triangles? And so we have a whole series of shapes that you can take these cross-sections of. Again, another fun exhibit. With the cone, you can do conic sections, get the hyperbola, parabola, ellipses, etc. We have some large puzzles. So this is a giant Soma set. You may be familiar with Soma, these cubes that form a 3 by 3 by 3 cube, but done on a large scale adds a new sort of social dimension to building it. This is a large burr puzzle, 6 pieces of wood that go together. This is a large puzzle with foam and magnets that it makes an interesting geometric shape, and it just sort of clicks into place beautifully when it's done. This I showed a minute ago is acrobats. So these pieces have little screw connectors in the hands and feet. You can put it together and make this large, colorful sphere. There's interesting combinatorics to the different ways you can do the color. So here we are after building it at this outdoor street fair. So as I said, we're traveling around the country. If you know anyone at a science museum anywhere that would like to bring this in, let us know or let them know. There's nothing really here in the Midwest near you that it's going to be at. Ohio, I guess, is the closest. So that's our traveling exhibit. What's the permanent museum going to be? And that we're working on. We have various kinds of concept sketches. So this is just to give people the idea that a museum of math can be a colorful place. It's not just, old books or just a slide rule or, Euclid's manuscript, but that it'll be a lively, engaging place that you can do all kinds of hands-on fun things. Here's a different kind of a sketch of what might be in there. So, for example, you can take this Menger cube. My laser battery is about dead here, I think. But you can take this Menger cube and you can slice it along a diagonal plane and get a very interesting cross-section. This might open up and let you see through it and let you crawl through it. Here you can take a 120 cell and turn that into a climbing structure that you can be inside of the shape. So 120 cell is one of these regular polytopes in 4 dimensions. Large mazes, all kinds of things. Here's an exhibit that I sort of like the idea. So imagine a disc over a disc with sort of bungee cords that you could open up and stand inside. But if the bottom disc could rotate, you could turn. And when you turn partway, all these straight lines now go diagonally. And they're still straight lines connecting top to bottom, but they form this curved surface, this hyperboloid like a cooling tower. So you could be inside this thing and have it get swollen. If you turn the base 180 degrees, it becomes a double cone and it just kind of squeezes you in there. We have all kinds of concepts. We're right now at the stage of whittling down through a list of hundreds of exhibit ideas that we have to try and see which will fit in thematically to make good groups, be cost-effective, safe. You don't want people to be choking on these things, etc. So again, this is just a concept sketch, not meant to be exactly what we do. But each of these things here has ideas behind them. So legally, in New York State, if you want to be a museum, you have to be approved by the New York State Department of Education. So we have our charter that allows us to use the word museum in our name. We have a website. You should go to momath.org, where we have lots of information on what we're doing and where we're going to be, etc. I write this column called Math Mondays for the museum. This is in the Make blog, if you just Google Math Mondays. So every Monday, there's some hands-on activity of something you can do. And this particular one was a bagel cutting technique. Some of you were at the bagel breakfast this morning. So there's a way to slice a bagel into 2 congruent pieces that are linked like a chain. Okay, so this is just a single bagel. I'll see if I can get it back together. So if you take your bagel and you slice it the right way, and it just takes a few seconds to do this, then you can open it up into these 2 pieces that are linked. Anyway, so this is one of the columns that we had on our Make Monday blog, and there's lots of other things, all of which is something that you can actually build. A few of them, we assume you have a rapid prototyping machine, but most of them are things you can do with convenient materials like bagels. We have a logo. In fact, we have a logo generator that allows us to generate a whole family of logos. So Chris Carlson, who's actually right here from Mathematica, came up with this idea for us, and it's proven to be very popular. But the idea is that our logo is not just a single logo, but it's a family, it's a space of logos. So what we have here is a symbol, in this case, say pi or other symbols, which is rotated and turned all different ways to give us your own personal logo by how you rotate it, how you slide it, how you adjust the spacing. We're looking at locations. Yes, question? It is not yet, but it will be on our website soon. It's written in Mathematica code, so it's something that you could use as a Mathematica player that anyone can have. And it will be public soon. Right now, we're in the design phase and the bidding phase for a company to revamp our website for us. So it'll be in the new updated website, maybe in 6 months. We're looking at sites in Manhattan, working with real estate agents and consultants. In Midtown, we're probably a month away from signing a contract at a place on 26th Street. So let me tell you how you can help make the museum a wonderful place. One is to give us ideas. So if you talk to me, I'm here for a while. If you have a concept for what you think will be a great exhibit, tell me about that exhibit. Other thing you can do is we have an advisory board, as I mentioned, of sort of faculty or industry mathematicians around the country. If you have ideas for people who should be on our advisory council, let us know. We always need people for our board of trustees, so these are the people that are more sitting on the financial side of things. And you can donate, you can give us money. So you can go to our website, momath.org, and you can click, and there's a place that you can enter a credit card. And so far, we've raised $15 million over from our initial $20 million. So this is definitely an activity which is getting great traction with people around the country, and it is definitely going to happen. We are definitely going to open. These are some concepts for possible future exhibits. I mentioned this bungee cord thing that you might stand inside of and spin the base around. This is something called the trammel of Archimedes. If you turn this crank, the handle forms an ellipse. So imagine, as the two little slides here go in the tracks, this thing forms an ellipse path. That could be really large, and the handle could be a unicycle, and you might sit on it and ride around and go in an ellipse path. Might be kind of a fun ride. Here's an idea for a light table that would allow you to explore packing. So there's many open problems of, how many, or what's the best way to put, 17 squares inside a triangle, or 6 circles inside of a square. You could, in real time, explore these problems, put these pieces together, and have the computer show you what your packing density is, and compare that to the best known, and allow you perhaps to be the world's record for a time in terms of, the best packing of 7 pentagons inside a hexagon. And we can have a big table of these, and you can feel that, in some sense, you're at the forefront of this mathematical question. We met with Martin Gardner about a year ago, shortly before he died, and asked him what he thought was the best thing to put inside of a math museum. And he thought puzzles of this sort, this is get off the earth puzzles, where you turn it, and the number of people start at one number, then they look like another number, and it's sort of an interesting sort of redivision of people. He thinks that those are very engaging. So if you have ideas for cool exhibits, let me know. Our concept is these exhibits should let people know that math is fun, math is exciting, that math is much richer than they've seen in the past. We like these hands-on activities where people get engaged, preferably in a whole body kind of way, that they're really in there, they're really doing things, not just something that could be delivered on a web page. If the content could be delivered on a web page, then there's no reason for them to come to the museum. So we want to have things that are physical and 3D and real. I think I'm supposed to stop around quarter after. Is that right? Is anyone here who knows when I'm supposed to stop? I could very quickly show you pictures of a big project I'm working on that I'm doing next weekend in Washington, D.C., I think in 1 minute. If I can see if I can just turn this into a web browser for 1 moment here. Let's see. So, is there a web browser somewhere? Okay, so next Saturday and Sunday in Washington, D.C. on the Mall, I'm doing a large outdoor public sculpture. This is the most ambitious one I've done yet. This will be a 2-day construction. The AMS, the American Mathematical Society, asked me to design something that people can come and build. This is made out of about 500 triangles, and all the triangles bolt together. Some of them are folded in the middle. I love these cool tunnels. If you look at this from different directions, you see there's tunnels that pass through it in all different crazy ways. There's these hexagon tunnels and square tunnels and different shapes of tunnels. All the parts are triangles. Most of them, or half of them are flat, half of them are bent. It's based on this underlying structure called the 10-3A lattice. This is a beautiful structure in space. You may be familiar with the diamond lattice. So the pattern of carbons inside a diamond, each one has 4 neighbors tetrahedrally arranged, and they make this structure. This is something like that, but much richer. It's been independently discovered many times, and people keep finding it and saying, here's this beautiful new structure. But it's been around a long time. I love this structure. It has all these wonderful tunnels through it. If I take each of these points, each one here has 3, each of these blue dots has 3 neighbors separated by 120 degrees. If I put a triangle on each side of those to sort of make a sandwich around those 3-fold points, I have this pattern of triangles that encapsulates the lattice. And each vertex is surrounded like this. So each vertex has 4 triangles meeting, 2 at triangle vertices, and 2 at triangle midpoints. So the triangles are not joined edge to edge. They have this sort of half-overlapping structure. If I take out the lattice and just have the triangles, I have this really nice form. And this is an infinite lattice. And I could derive it also from this packing of tetrahedra and octahedra. And if I take a finite chunk and want to seal off the edges, I just have to bend some of these triangles a bit. And I can then use this around chunks of space in all different ways. I won't say too much. You can make paper models of it. You can make a zone tool model of it. These are the test pieces, laser cut, various brackets for these 2 different angles. Here's making one of those connection points out of metal. Some other test pits. This is a 3D printing using a Z-Corp printer. So Z-Corp makes a kind of 3D printer that prints color. So this is a model of it. Another view showing some of the tunnels. I've since gotten all the pieces and test fitted. So here's the beginning of how the sculpture will look like. So next weekend in Washington, D.C., I'll have these 500 pieces and nuts and bolts and screwdrivers, and anyone can come help me build it. So on my website after that, you'll see pictures of whether it succeeded or not. So I think I should stop there and say, if there's any questions, I don't know how much time we have for questions. I'm happy to answer any questions. Yes? How often do my public projects succeed or fail? So I've never had a failure yet, okay? I always worry about all the things that can go wrong. I never know quite how long it'll take. But I learn things along the way, but yeah, I've never had anything completely crazy. I've never had somebody walk off with key pieces. I've never had anything break or get terribly scratched. So maybe I've been very lucky. Maybe next weekend will be a huge catastrophe. We'll see. That's sort of the excitement for me in this. I mean, the worst that happens is that it only gets half built and we continue it somewhere the next week. So, I mean, it won't be terrible, I tell myself. But I do worry about many, many possibilities of what can go wrong. I try to plan and engineer as much as I can. As you can tell, all my work is incredibly designed ahead of time. But, engineering always comes up with surprises. Yeah. No, the parts are all identical. They don't have to be labeled. No, half there's flat and there's bent, and then there's 4 colors. So, I mean, those are the 8 possible parts. Yeah. Other questions? This is 42 inches, the sculpture. So it's going to be installed. The AMS has funded this, and they donated it to Towson University, so it'll be on public display at Towson. So next Monday, I'm bringing it there and giving a little talk and an opening presentation, and maybe finishing it if there was problems. Yeah. Other questions?